Welcome to our class once again. We are still considering wave. In this video, we'll be looking at the first part of wave equations. There will be another video where we look at the second part of wave equations. In this video, we'll be looking at the common wave equation that we know. Then the next video we're looking at the other equations that are also used in treatment of waves. I will be showing us the outline, what this first part covers. Looking at what wave equation means. Then we'll look at the types of wave equations, how this wave equation is represented. Then we'll look at the aggregation of the parameters in the wave equations. Now, what does it mean to have wave equations? Wave equation. Now, wave equations are mathematical tools for expressing or describing the behavior of various types of waves. Any type of wave that you can think of can be represented mathematically. So any mathematical expression for representing any type of wave is a wave equation. A wave function. We have examples of these waves, which include water waves, sound waves, seismic waves, and other classes that are mechanical, that needed material medium to propagate, and also other waves too that do not need the material medium to propagate, such as light waves, radio waves, X-rays, and other classes in that spectrum. So types of wave equations. We have two. We have what is called the progressive wave equation and what is called the stationary wave equation. So progressive wave equation describes equations that are progressive. So this equation describes waves that are progressive. By progressive wave, we mean wave that their propagation is not impeded by any form of barrier. That is, when such waves propagate, they don't encounter any interface or boundary that could reflect it. Those are progressive waves. Progressive waves propagate in the medium without encountering any form of boundary or interface. So progressive waves are unidirectional because it's one direction, it's not reflecting. So it's unidirectional, just one direction from the source and away from the source. And also they carry energy and momentum from the source of the wave along as it propagates. So from one point A to point B, point A being the source, point B being the reference point in space. So they carry energy as it propagates in space. Now, examples of waves that are progressive are sound waves, light waves, water waves, and so on. So you see, progressive wave could be electromagnetic and could be mechanical. You see, progressive waves are some electromagnetic waves that are progressive, and there are some mechanical waves that are progressive. For example, water waves, sound waves, and mechanical waves. But light waves It's electromagnetic. Okay, so note that. Then we have the second type of wave equation, which is the stationary wave equation. And this equation describes propagation of wave that could not progress or propagate forward. So therefore, they move back and forth. They move back and forth in both directions. They propagate, they are reflected back, probably due to a boundary or a interface or an interface. And such type of wave, stationary wave, exhibit what is called standing wave pattern. So that's why stationary wave are also called standing wave. Some refer to stationary waves as standing waves. And this equation that describes this type of wave is called the two-way wave equation. We still see it as we go. So one of the ways to identify stationary wave and propagation is that for both types, progressive wave and stationary wave, the nodes are fixed. The nodes are fixed. You see the nodes, this point of minimum displacement. Here you have the equilibrium point. But unlike in the progressive wave, where also the point of maximum displacement, the amplitude is constant. Stationary wave, the amplitude is not constant, it varies. So the antinodes, the point of antinodes are not fixed. The amplitude, the maximum displacement varies. It's not fixed. As the wave goes back and forth, then the antinodes is not obtained at the same point. So the antinodes is not fixed, while the nodes are fixed. And that's why we say they are bidirectional, back and forth movement, bidirectional. And it is obtained by the superposition of the forward going and backward, overlapping of the forward and backward waves. Overlapping. Because of that, there is no propagation of momentum because the wave is not progressive. It's not traveling beyond a confine. Then there is no energy or momentum transfer. Examples of such type of waves, stationary wave, are waves in a plug string or waves in a pipe. Look at it. This is lambda over 4. This position of x1, if x1 is here, that's lambda over 4. Because this from here to here is lambda. Here is lambda over 2. Here is lambda over 2. Then here will be lambda over 4. And x2 we say is 5 lambda over 4. This lambda, then here. So that means s2, we assume our s2 to be like this. So lambda, 5 lambda over 4, and this is lambda over 4. So we want to see the phase difference between, if O is here and if our P is here. And from what we saw, the answer there is equivalent of, that's crest to crest. Okay, that is what we have there, which is this. So phase difference there is 2 pi. That's a cycle. Which is equivalent of 360 degrees, 2 pi radians. Okay, so that's what we have here. I believe that explanation will help. understand. Just add further explanation too. Okay, for example, if we have at t is equal to 0, we have x is pi over 2. The difference between two particles is pi over 2. This pi over 2. Here, this pi over 2. So if one particle is here and that particle is here, then if you obtain it, your phase difference will be pi, which means the particles are out of phase. Look at it, they're out of phase. Though they are on the same line, but when one is rising, one is coming to, one is going to maximum, one is coming to minimum. That's meaning of being out of phase. Out of phase. Okay? And when the distance between them is lambda, that means we have one here and we have another one here. X1 and X3 now. This is lambda. What happens? Then the particles are in phase. What does that mean? They are in phase. They are both on the same line. This one is going to maximum at S1. S3 is also going to maximum. It's going to maximum. They are in phase. So the equation have these variants, different forms, and we express different forms. Beginning with this, then it can be expressed also as this. Remember, omega t minus 2 pi over lambda x. Okay? Then 2 pi ft, because omega is 2 pi f. Yes. Then factorizing, then f is 1 over period. We have it inverse of the period. Then also 1 over period is equal to v over lambda, or f is equal to v over lambda. We have the then factorize 2 pi lambda. So this it can be in any of this form. Any of this form. And if questions are given, we have to expected to estimate any of the parameter, and you need any of this equation, you look at the question critically and you compare with any of the equation that is identical or close to the equation given in your question. That's what you do. That means you must master this equation. So when question comes, you look at which one is close to it, you compare, and from there you solve. We see examples as to go on. Okay? So again, you can also determine from the displacement of the particle in the medium, you can determine the velocity of the particle in that medium, which is differentiating the displacement with respect to time. You have this, and the maximum displacement will be this. But maximum displacement, or maximum velocity rather, cos this will be equal to 1. Equal to 1. That is everything here will be 0. Then we can also determine the particle acceleration, the shape of the particle of the medium. I'm differentiating the velocity again with respect to t, or the displacement with respect to t 2 times the second derivative of displacement with respect to time. So we have this expression also, and the maximum acceleration of the particle now will also be this, where this is also equal to 1. I have maximum acceleration when the sine of the phase angle is equal to 1. Sine of course phase angle is equal to 1. That's it. And so I think I've shown us this. We can work with this expression. We will still, well, at an higher level, we will still come back to working so much with this expression. But for now, that's not our interest. But very shortly, we'll be looking at a similitude of this expression. A similitude, we still get it, or that expression. This is what we'll be working with later in the next video. We are talking about the two-way wave equation. Let's bring this to familiarize yourself with that equation. Probably want to study how this equation was derived. Okay? Thank you. So the period and the parameters now in the equation, this is what they mean. Each parameter, y again is the displacement of the particles, the medium, a the amplitude is the maximum displacement of the particle on the rest position, phi is the phase difference between the particles, omega is the angular frequency of the progressive wave, which is measured in radian per second, then f is the frequency of the particle, is per second, s is the distance traveled by the wave from the source or origin, it's in meters, then t is the time taken to cover the distance, which is in seconds, lambda is the wavelength of the progressive wave, which is also measured in meters, then v is the velocity of the progressive wave, which is measured in meter per second. I believe you are familiar with all these things, but just as a reminder, please note they are all a standard unit. So when you are working, or else if all units are not a standard unit, or sorry, all units are, if it's on the graduate question and you have you check your answers it's in SI unit, then all your units you work with must be in SI units. Okay, please be sensitive of the unit, that you will not use the wrong unit in your estimation.